Hi, Albert here. Welcome to another episode of Matrix Champs. Today, we'll be talking about determinant. Not this from your quadratic equations, but this in matrices. However, what are determinants? Since the Babylonians, linear equations have been a field in mathematics. However, the first instance of a matrix was in China in 200 BC. Determinants were first found and studied extensively in Japan in 1683. Then, not soon after, in 1693, the determinant was also discovered in Europe by Leibniz. It was used as a means to determine if linear equations had solutions. This term was coined by Cauchy, but before, Kramer and Laplace had already popularized its use. The determinant is a value derived from a matrix that is special to square matrices. Kramer's rules dictates how to find the value of a determinant from a matrix. For example, for a 2 by 2 matrix, it is nearly the difference of AD and BC. For a 3 by 3 matrix, you have to conduct a Laplace expansion, which leads to smaller cofactors that are themselves also determinants. Generalizing, Laplace expansion also includes other n by n matrices. We just have to note the terms Mij as the cofactor of a coefficient Bij, in which I is the row and j is the column. As such, the determinant for any matrix n by n is the summation of I equals 1 to the n of the coefficient Ij multiplied to negative 1 to the I plus j power multiplied again to the cofactor Ij. In which case you have to make constant I or j, meaning that your coefficients will have to follow one row or one column. Typically, matrices also have the following properties. For example, the determinant of the identity matrix is equal to 1. Exchanging rows within the matrix makes the new determinant equal to negative of the previous one. Adding a row to another row within the matrix does not change the determinant. The determinant is also equal to 0 if two rows of the same matrix are equal. The determinant of a transposed matrix is the same as the original one. Then, if A and B are two matrices with the same number of rows and columns, the determinant of AB is equal to the determinant of A multiplied by the determinant of B. Finally, multiplying a row by k also scales the determinant by k. One way to visualize this is to let matrices be composed of vectors. In this case, let's use the 2 by 2 matrix so that it's easier. Thus, the matrix A, B, C, D can be converted to vectors AB and CD on an x by y plane. In such a case, the determinant is therefore the side area of a parallelogram between the two vectors. Then let's begin. As we can see, the determinant of the identity matrix, which has 1, 0, 0, 1, can be converted into vectors 1, 0, and 0, 1. It creates an area that is equal to 1. Meanwhile, switching the rows of the matrix changes the direction of where we're going to look at it. Thus, the sign is changed, but the overall magnitude is the same. Meanwhile, adding one row to another in a matrix only skews the shape. It doesn't change the area and therefore the determinant. Then, if two rows are the same, you'd see that it doesn't actually produce an area, therefore the determinant is 0. Transposing the matrix only flips the shape and doesn't change the area, therefore the determinant is still the same. Then, multiplying one row by a factor of k actually also enlarges the area by a factor of k. Thus, the determinant is also multiplied by a factor of k. Finally, let's solve one of our own. First, we switch to rows. Then, we expand it using the Laplace expansion. We transpose to make use of the 0, and in one cofactor, we switch to rows. Then we simply solve and simplify. And that's it for another episode of Matrix Traps. Thank you for watching. For more of our videos, click to the subscribe button.